Real-world network configurations are complicated. Outages and data breaches can occur when configurations drift. Oracle Cloud Infrastructure's Zero Trust Packet Routing provides human-readable security policies independent of and in addition to network configuration. Zero Trust Packet Routing continues to protect data even when accidental drifts in network configuration may expose internal systems and sensitive data. Hello, everyone. I'm Pradeep Vincent, SVP and Chief Technical Architect at OCI. Security has always been a top priority for OCI. We take pride in protecting your data. The greatest risk to your data is how it moves. I'm excited to talk about a paradigm shift in cloud security. Working with our collaborator, Applied Invention, OCI is launching a new product called Zero Trust Packet Routing, abbreviated as ZPR, for representing and enforcing customers' data security intention. Today, in any cloud, network access to your data is secured by a bunch of network routing policies and network security policies. And this applies to data that resides in database, an object store, or really any other store. Ideally, the network operators manage network policies, and the security operators enforce security policies. However, with typical network policies, the security aspects and the networking aspects of those policies are commingled. If network policies change, any security policies defined at the network level can be affected in ways that are hard to predict and evaluate. This can result in security gaps and vulnerabilities. A more robust approach is to define network-level security policies in a way that is not dependent on the network topology. Information security policy should capture the intention of what should happen to the information and where it can go. And that enforcement of that intention is an infrastructure problem that OCI has to deal with. Now, we could have come up with Oracle proprietary solutions for this problem, but infrastructure security works best when they're not proprietary designs. At OCI, we prefer to compete on superior performance, pricing, and implementation rather than locking a customer in with proprietary standards. Oracle and Applied Invention have been collaborating on ZPR. I'm super excited to welcome Dr. Danny Hillis to join me in introducing ZPR. Dr. Danny Hillis needs no introduction, but I'll give one anyway. He's a legendary computing pioneer and co-founder of Applied Invention. Dr. Hillis has contributed to many foundational ideas in modern computing. He co-founded Thinking Machines Corporation to turn his work on massively parallel computing architecture into supercomputers called connection machines. Dr. Danny Hillis, thank you for joining me.
Oh, thank you, Pradeep. It's good to be here.
All right, so in 2013, you gave a TED Talk with the provocative title, "The Internet Could Crash. We Need a Plan B." By the way, it was a really good TED Talk. You talked about how internet and networking is fundamentally built on trust. Can you tell me more about security paradigm or the modern day networking?
Yes. I mean, when the internet was first built, there were a fairly small number of people on it that all kind of knew each other. Certainly the system administrators all knew each other. So the protocols of the internet were kind of built with the assumption that the system administrators were all good guys. And, maybe a user would accidentally do something bad, but we didn't imagine that the users of the internet would be a problem. We didn't trust the phone company. And so the internet is very good about, dealing with problems of communications lines going down. But it was an explicit decision to not have the internet have any security within the network itself. All of the security was supposed to be in the endpoints, which, was login security in those days. And that decision actually, I think, ended up being a mistake. Or maybe it wasn't a mistake because it got the internet started faster. But from the standpoint of modern security, it's a mistake because the internet is fundamentally shifting around a bunch of anonymous packets that can claim to be wherever they want to claim to be from. And, there's no real way when you get a packet to know who it actually came from. And so that's the foundation on which all of our security is built. So a few years ago, actually, I got together some people that I'd worked with for decades, and we kind of wrestled with this problem. And we sort of asked the hypothetical question: how would we have designed the internet if we had known what we know today? We knew modern security techniques. We knew the problems we had today, and we realized that would really make a very different protocol down at the bottom at the IP level. And fundamentally, we would make the internet have policies about who was allowed to talk to who. And those policies would be enforced in the network itself. Now, that's completely against the philosophy that the internet was designed in the first place. But it seems almost obvious today that might be a better idea. So that was kind of the beginnings of Zipper.
Yeah, that's very insightful. Yeah, I mean, if I think about it, networking does feel like a house with 100 doors, and we are trying to somehow secure all of them and wonder why it's not that robust. I remember dealing with BGP route advertisement issues, wondering why a small operator somewhere in the internet is able to inject a faulty route and take down big parts of the internet. It really is bizarre to me. So what's the big idea behind Zipper?
Well, so I think you sort of that bizarreness that you said was a part of it. I mean, it doesn't make any sense, for instance, to have all the security cameras in the world be able to do a denial of service attack on, my home computer or something. The internet shouldn't handle that traffic. So really, the network itself should have policies. So an enterprise, for instance, should be able to say, here's the policies for my network is who is allowed to talk to who, how much, what services are accessible from what places, by using what equipment, things like that. And so instead of trying to deliver everything to everything by default, it only delivers things that are compliant with policy. And then it turns out that you can do that if you just change the protocols a bit. That's what zero trust packet routing is about. Every packet actually carries kind of cryptographic guarantees that it was sent by who it claims to be sent by, and it's been authenticated and the receiver is authenticated, and that it's compliant with the policies of the network. So it's kind of an independent level of security that isn't in the endpoints. And so it can work in conjunction with all the kind of security that we're used to about kind of TLS, level security, login security, all the firewalls that we have. All of that can still stay there, but Zipper provides this other level of protection, and that fundamentally makes it easier to secure your system.
So how does Zipper address the performance security trade-off?
So these days, computers are a lot faster than they were when the internet was designed. So you can do a lot more in a computer and still keep up with wire speed. And in fact, Zipper does have some extra work that it does, the first packet that goes through to establish that security relationship and kind of authenticate the sender and the receiver. But once that packet is through, it can actually, in the data plane, shift the data through at extremely fast rates. So in some ways, it is simpler than what IP does, because once it's established that packet, it can kind of cache things.
Well, that sounds great. Well, OCI cares a lot about security, but we also believe security should work across clouds and multiple platforms. Can you tell me a little bit about how Applied Invention is working to standardize Zipper?
Yes. Well, of course, eventually enterprises are going to want to have this level of network security across all of their computing resources, on-prem and all the various clouds that they use. And they're going to want to be able to move services, from implementation one place to another. They want to be able to move them around without changing the security rules. So the way that zero trust packet routing is designed is it's really designed to be an open standard, so that all these things are interoperable using the same protocols. And an enterprise can have basically a set of security policies that apply to all of the things on the network
Well, that sounds great. Well, Zipper is just the latest collaboration for us at Oracle with Dr. Danny Hillis. But this isn't the first time. Oracle has acquired various parts of Thinking Machine, and Danny has worked on Sun data center modules as well in the past. So thank you, Dr. Danny Hillis, for taking the time to share your perspective with us.
Oh, it's a real pleasure, and I'm very excited about Oracle's implementation of Zipper.
All right, that was great insights from Dr. Danny Hillis. So to take these abstract ideas into a practical problem and solution, let's walk through an example experience. Let's imagine a hypothetical company called Supremo. They launched a novel monitoring device that collects sensitive data from various sources to provide insight to the users about their local environment, while also producing useful data for the scientists. Supremo has designed a service with cloud security best practices in mind, including strong data and network isolation. The private and sensitive data resides in a central database, which is isolated from customer traffic and the internet. Data for customer access is aggregated into a separate public database. Selected scientists have sensitive data access via the Science app or VPN connection. Let's focus on the central database and the Science app and take a closer look at the networking and security configuration. The network and security policies for Science app allows access to the Science app from select IP CIDR ranges over the VPN, and no direct access whatsoever to the central database. The IP CIDR range is where the limited set of scientists are expected to initiate network connections from when they talk to the Science app. These policies ensure that the sensitive data is kept very secure. Time passes. The app becomes more successful, and more devices come online, and more scientists are attracted to the data. But the VPN-based access becomes a major source of friction. To simplify onboarding, the team builds a restricted internet access approach with tight IP constraints. Now, the sensitive data access is still secure so far. More and more users request access. Now what happens? The beleaguered team continues to expand access, but the network security group policy for the sensitive database and the Science app becomes too complex and cumbersome to manage. Complexity breeds security holes. What was once a clear set of network configuration and security boundaries now has an unintentional hole exposing the sensitive database to the internet. And critically, the complexity gets in the way of the security operator from catching the security issue. Now, you may think, hey, this is just a theoretical concern in a theoretical example, but think again. Misconfigurations in the cloud has resulted in data leaks in the past stemming from errors in network configuration. Cloud platforms often push this aside as a customer error that they can't do anything about, but we disagree. As a cloud platform, we fundamentally need to offer the products and the primitives that make customer security posture robust. Now, the existing network security primitives are based on networking constructs such as IP addresses. Network-based security policies have an inherent dependency on the network configuration and policies. But do they really need to be coupled this way? Well, in order to make the security posture robust, we need security policies that are enforced at the network level, but yet managed independent of the network policies. The network admins need the ability to change the network policies without violating the security policies. And the security policy administrators and auditors want the surety that the security policy will be enforced independent of the chaos in the network policy changes. Zipper is our next generation security platform that enables customers to define and enforce intent-based network security controls. Customers define an intent-based security policy called Zipper policy. that humans can easily read, audit, and understand. Zipper platform translates your intent into the right set of underlying rules and distributes the network rules to the right endpoints. The endpoints then enforce the rules, and Zipper continuously watches all the system changes to ensure that the security intent is in fact enforced. In the future, you'll also be able to audit, validate, and visualize the policy enforcement across your network. Zipper-related network rules, as well as traditional network configuration policies, are implemented by OCI concurrently. But keep in mind, the presence of Zipper policy in a network immediately confirms all the traffic needs to be permitted by the Zipper policy, in addition to being permitted by other network policies. Now, let's return to the Supremo example and see how they use Zipper to make their security posture robust. First, they have tagged their resources with the security attribute. Compute instances running Science app are assigned the attribute AppScience, and the database instance is assigned the attribute database sensitive. Next, they have activated Zipper by writing one or more Zipper policies, and now the virtual network only permits the network packets allowed by the Zipper policies to flow through. Let's look at the database that has sensitive information. Only if there is a Zipper policy allowing connectivity to the database with security attribute sensitive will that network connection be allowed at all. This policy statement allows any application host with security attribute signs to make a SQLnet TCP connection to the database with security attribute sensitive. Any other traffic to the database would fail, regardless of the network configuration. Now, as before, Supremo goes through its phases of success, and network configuration gets complicated and more complicated, eventually resulting in a security hole. But the fundamentals of architecture did not change. The principles around who should have access to the sensitive data did not change. And so there's no change to the initial Zipper policy. And the Zipper policy negates the security holes introduced by the network configuration. The key here is that the security design now has a mechanism to describe what can talk to what in a human-readable language, independent of the IP addresses and the IP routing configuration. The intention expressed in Zipper policy is durable to the lifetime of the architecture, not to the current network state. By using access control security attributes rather than naming or IP addresses, the specifics of the infrastructure remain elastic while preserving the security posture. In separating the security policies from the network configurations, they can now be enforced, validated, audited, completely independent of the network topology and network configuration. So how does Zipper work under the hood? Well, Zipper policies are first written by customers and they are recorded by the Zipper control plane. Subsequently, the Zipper service translates these policies into a machine-oriented intermediate form that includes a set of Zipper security attributes and a set of Zipper network rules. Now, the Zipper service uses OCI VCN service to push out the Zipper security attributes and the Zipper network rules to the OCI network for enforcement. Network traffic passing through a Zipper-enabled network gets annotated with content-appropriate Zipper security attributes. Every network flow originating from compute instance is annotated with Zipper IDs corresponding to the security attributes of that compute instance. Outside traffic is annotated as such. So let's go back to our example. Now, the network traffic from the internet is annotated with a different Zipper ID compared to the network traffic from AppScience compute instances. And these Zipper IDs are not dependent on the IP addresses on the network packets. That's quite important. Each network decision point uses the annotated Zipper IDs to determine whether the Zipper network connection complies with the configured Zipper policy. This evaluation is independent of other network configurations that are applied to the network packets. When it comes to network packet level security enforcement, the performance impact is always a concern. ZPR is implemented to have no real impact on network performance. ZPR directives are about the network flow, not the network packets or the packet contents. So ZPR policy evaluation is performed during a flow establishment, and the results of that evaluation are cached. The cached results are used for processing network packets of all established network flows, and as a result, ZPR policy evaluations don't have any noticeable network latency or throughput performance impact. We are excited to bring you OCI ZPR. Here are some of the key takeaways. IP network was architected to thrive in a trusted environment, and security was bolted on as an afterthought. Current network security in the cloud is not robust enough for security-conscious enterprise customers that have data in the cloud. ZPR marks a paradigm shift in cloud network security. Shifting security to an intent-based data-centric security solution is fundamentally more robust. ZPR is built using an open standard that can be used across multiple clouds or even on-prem environment and hybrid environments. Thank you for joining me today. See you next time.